Hello students, in this video we are going to continue second lecture on topic unsymmetrical fault analysis. As we had already discussed during the last lecture, the content of the unsymmetrical fault analysis chapter are nothing but method of symmetrical component, relationships, sequence impedances, representation of the power system by positive, negative and zero sequence network, nature of sequence impedance of the power system component, then line to ground, line to ground fault, and analysis of unloaded and preloaded alternator and simple power systems with and without fault impedance. During the last lecture, we had discussed about what is the meaning of fault, what are the different type of the fault present in the power system, what is meant by the symmetrical fault, what is meant by the unsymmetrical fault, and we had started with method of symmetrical component. So just we'll revise the part which is already covered during the last lecture. We had discussed that fault is nothing but it is an adverse condition in case of the power system due to which the current is diverted from its intended path. Then we had discussed about different type of the fault, that is symmetrical fault and unsymmetrical fault, and we had discussed that in case of the symmetrical fault, examples are triple LG and triple L fault. There is unsymmetrical fault are the faults which are unsymmetrical in nature and give rise to unsymmetrical current, such as different current in the three phases. An example of the unsymmetrical fault are line to ground fault, line to line fault, then double LG fault, and phase to phase and third phase to ground fault. Then we had discussed about what is the purpose of the unsymmetrical fault analysis, and we had discussed that the purpose of the unsymmetrical fault analysis is nothing but the information obtained from the unsymmetrical fault analysis is necessary for the determination of rotative gear relay setting and in studies of transient stability in an interconnected power system. And in case of the method of unsymmetrical fault analysis, we had discussed that since unsymmetrical fault causes the imbalance in the system, and that's why mostly what we do, we convert unbalanced system into the balanced system with the help of the symmetrical component. And whenever the analysis is completed, then again this balanced parameters again converted into the original one. So what is meant by the symmetrical component? Method of symmetrical component is very powerful approach and has simplified the procedure for solving problems on unbalanced polyphase system. This method is valid for any number of phases, but the three-phase system is of main interest because whenever we are going to do the unsymmetrical fault analysis, mostly we consider the three-phase system. And this method of symmetrical component was proposed by C.L. Fortis in the year 1948. So, if we are interested in the definition of the symmetrical component, according to the Fortescue theorem, any unbalanced three-phase system of current voltages of other sinusoidal quantities can be resolved into three balanced system of phasors, which are called as the symmetrical component of the original unbalanced system. Such three balanced system contribute three sequence network, which are solved separately on single phase basis. Once the problem is solved in terms of the symmetrical component, it can be transferred back to the actual circuit condition by superposition or phasor addition of these quantities. Thus, in short, the symmetrical component helps to convert unbalanced system into the balanced one for the analysis purpose, and once analysis is done, then again it is converted into the original one. So, next point is symmetrical component of three-phase system. Now the symmetrical components differ in phase sequence, that is the order in which the phase quantities goes through a maximum. Now this balanced set of components are divided into three components. First one positive sequence component, second one negative sequence component, and zero or uniphase sequence component. That means when we are going to do the unsymmetrical fault analysis for converting the unbalanced system into the balanced one, we have to calculate three main components: positive sequence component, negative sequence component, and zero or uniphase sequence component. So first of all, what is meant by the positive sequence component? The figure here shows the phasor diagram for the positive sequence component. The positive sequence system is that system in which the phase or line current or voltages attain a maximum in the same cyclic order as those in a normal supply. So positive sequence component are mostly marked by the subscript 1. That means suppose A1, B1, C1. These are the positive sequence component for A, B and C phases. The three phases of the positive sequence system are of equal magnitude, spaced 120 degree apart, and may be represented in complex form as follows. That is, A1 is the positive sequence component for A phase. B1 is the positive sequence component of B phase. And what is the relation between A1 and B1? B1 is equal to A1 at an angle of minus 120 degree. Or it is also represented as capital A1 e raised to minus j2 pi by 3 or small a square A1, where and C1, that is the positive sequence component of the phase C, is having the relation with A1 as C1 is equal to A1 at an angle of 120 degree or A1 e raised to j 2 pi by 3 or small a A1. So what is the, here another term is added, that is small a. What is meant by the small a? The complex number e raised to j 2 pi by 3 in above expression is called as the operator of the three-phase system and is denoted by letter small a. Multiplication of the phasor small a or e raised to j2 by 3 turns into through 120 degree in counterclockwise direction. Multiplication of phasor by a square or e raised to minus j2 pi by 3 turns it through 240 degree in the counterclockwise direction. And the position of phasor remain unaltered if the multiplied by the a cube. Whenever we go through the relation for positive sequence component, negative sequence component, zero sequence component, their formulae, and whenever we go to solve the problem, at that time we have to multiply by a or a square or a cube. At that time, just keep in mind that multiplication by a, that means we have to multiply it by 120 degree angle. Then multiplication by a square, that means there will be 240 degree displacement, whereas a cube is nothing but equal to the 1. Now, what is meant by the negative sequence component? The phasor diagram is shown here for a negative sequence component. You can see the difference between the phasor diagram of positive sequence component and negative sequence component. So, what is the definition? Negative sequence system is that system in which the phasors still rotate anti-clockwise but attain a maximum in reverse order, such as A, C, B. In last case, that phase sequence is ABC, but in this case, it is a, C, B. This sequence only arises under condition of unbalance as when unsymmetrical fault occur. Negative phase sequence components are marked by subscript 2. That means capital A2, capital B2 and capital C2 are the negative sequence component of A, B and C phases respectively. The three phases of the negative phase sequence, unlike positive sequence system, are of equal magnitude and spaced 120 degree apart. They are represented in the complex form as capital A suffix 2 is nothing but negative sequence component for phase A. B2 is the negative phase sequence component for phase B. And what is the relation between B2 and A2? B2 is equal to A2 at an angle of 120 degree or A2 e raised to j2 pi by 3 or it is A square A2. And C2 is nothing but negative phase sequence component of phase C. And what is the relation between C2 and A2? C2 is equal to A2 at an angle of minus 120 degree or A2 is equal to e raised to minus j2 pi by 3 or it is represented by small a square A2. Now the last phase sequence component is zero phase sequence component. The phasor diagram is shown here for zero phase sequence component. Zero phase sequence system in a single phasor system combining three equal phasors in phase as shown in the figure and represent the residual current or voltage present under the fault condition on a three-phase system with fourth wire or earth return present. That means in this case the fourth wire or neutral wire is present. And zero sequence component are marked by the subscript 0. That means A0, B0 and C0 represent the negative phase sequence component of phase A, B and C respectively. Now if we go through the relation or if we are interested in the deriving the formula for positive, negative and zero sequence component of phase A, then we have to go through this relation A0, A1, A2 is 1 by 3, then matrix 3 by 3 matrix into ABC, then we will get these formulas. Now, but before discussing this formulae, Now we will consider the positive sequence impedance, negative sequence impedance and zero sequence impedance. In exam there is repeatedly asked question. Define and derive the formula for the positive, negative and zero sequence impedance. So what is meant by the positive sequence impedance? The impedance of the network opposed to the flow of positive sequence current is called as the positive sequence impedance. See, uh, that is positive sequence impedance is nothing but it is the because it is the opposition to the positive sequence current, and as we are having the idea that positive sequence component is represented by suffix 1, so here positive sequence impedance is nothing but z suffix 1 and it is having the formula 1 by 3 of za plus azb plus a square zc. Then negative sequence impedance. What is the definition? If only negative sequence current flows, the impedance of the network offered to this current is called as the negative sequence impedance. And we are having the idea negative sequence impedance is represented by suffix 2. That's why the formula is Z2 is equal to 1 upon 3 ZA plus A square ZB plus AZC. And what is the definition for zero sequence impedance? The impedance offered to the zero sequence current is called as the zero sequence impedance of the network. And we are having the idea that zero sequence impedance is represented by suffix 0. That's why formula is Z0 is equal to 1 upon 3 ZA plus ZB plus ZC. So for the examination point of view, you should have the idea about the definition of all these three sequence impedances. You should have the idea about the formulas also, because in exam there is a repeatedly asked question either related to the theory or there might be the numerical, and you have to calculate this positive, negative and zero sequence impedance. Of course, you have to practice more numerical for the examination point of view, but for this video lecture, we'll consider one example, that is compute symmetrical component of the three-phase voltages where voltages are given by VA is equal to 100 at an angle of 0 degree, VB is equal to 110 at an angle of minus 100 degree, and VC is equal to 115 at an angle of plus 110 degree. So first of all, we have to calculate the positive sequence component, because we are having the idea that symmetrical component is nothing but positive sequence component, negative sequence component and zero sequence component. So what is the formula for positive sequence component? Positive sequence component, that means it will be denoted by suffix 1, and since we have to calculate the voltage, it is V suffix 1. If the question is related to the calculation of current, it will be I suffix 1. So here in this case, V1 is equal to 1 by 3 VA plus AVB plus A square VC. Now you are having the idea about the what is the meaning of A and what is its value, that we had already discussed. So here what is the formula? 1 by 3 VA is 100 at an angle of 0 degree, which is given in the numerical only, plus VB is 110 at an angle of minus 100 degree, and since we have to multiply it by factor A, and we had already discussed A means we have to multiply it by 120 degree, that means angle will be added into the polar form, and it will be minus 100 degree plus 120 plus A square VC. So VC is 115 at an angle of 110 degree. Since we have to multiply it by A square, that means plus 240 degree will be added into the angle 110 degree. So if we calculate, we will get the positive sequence component equal to the 105.7 at an angle of 3.19 degree volt. So we had calculated the positive sequence component in the first step. Now next step, we have to calculate the negative sequence component, where again having the formula V2, negative sequence component is represented by the suffix 2. That means V2 is equal to 1 by 3 VA plus A square VB plus ABC. That means you should have the idea about these formulas. Then we have to just put the values, and here A square we have to add plus 240 degree, here we have to multiply by A, add 120 degree in angle, and you will get the negative sequence component VT is equal to 20.24 at an angle of minus 163.35 degree volt. Now last component, zero sequence component. What is the formula for zero sequence component? It is represented by suffix 0. V0 is equal to 1 by 3 VA plus VB plus VC. That means the multiplying factor A will not be present in this formula. So just you have to put all the values which are given in the example, and you will get the zero sequence component 13.86 at an angle of minus 0.37 degree volt. But for you have to practice more number of numericals from the JB Gupta book as well as from the Nagrath Kothari electrical power system, sorry, modern power system analysis by Nagrath Kothari book. Now, in your syllabus, another one point, representation of the power system component by in terms of the sequence component. So here mostly we consider the example of synchronous machine and transformer. Sorry, synchronous machine and transmission line to represent the system in terms of the symmetrical component. So here the next point is sequence impedances and network of synchronous machine. See, the word is synchronous machine. That means here you can consider the synchronous generator or synchronous motor. That's why this is the generalized term synchronous machine. So here we have to show the sequence impedance and network of synchronous machine. In example, there is repeatedly asked question. Draw and explain the positive, negative, and zero sequence network for the synchronous machine. So first of all, we'll refer the diagram. Here, three-phase synchronous generator with grounded neutral is shown. That is, the EMP generated by all the phases, that is A, EB, EC is shown. Then reactance of the three phases shown in series with the EMF. Then in case of the neutral, the reactance is impedance of the neutral wire is Zn, and under the unbalanced condition, current flowing through this system, that is whenever the unsymmetrical fault is occur, the current IA, IB and IC is flowing through the phase A, B and C respectively, whereas IN is the current flowing through the neutral. Now, if we go through the relation, here IN is equal to IA plus IB plus IC. Now, here we have to calculate the positive, negative and zero sequence component. So, first of all, we'll discuss about the positive sequence component. But before that, just keep in mind that here what we'll do, we'll calculate the positive sequence component in this case, and it is represented for the three-phase system as well as since that system will be balanced one, we can show in terms of the single phase basis also. So first of all, we'll consider the positive sequence network for the synchronous machine. Since a synchronous machine is designed with symmetrical winding, it induces EMF of positive sequence only, such as no negative or zero sequence voltages are induced in it. When the machine carries positive sequence current only, this mode of operation is the balanced mode. The armature reaction field caused by the positive sequence current rotates at synchronous speed in the same direction as the rotor, such as it is stationary with respect to the field excitation. The machine equivalently offers direct axis reactance whose value reduces from subtransient reactance XD double dash to transient reactance XD dash and finally to the steady state synchronous reactance XD, which is similar to the short circuit transient process. We had already discussed during the lecture hour, that is how to show the short circuit fault waveform, that is how to show the subtransient reactance, transient reactance and steady state reactance. Then we had performed the experiment also based on this concept. So if armature resistance is assumed negligible, the positive sequence impedance of the machine is shown in terms of the Z1, that is positive sequence impedance. Z1 is equal to JXD double dash, that is subtransient reactance if one cycle transient is of interest, because we are having the idea that initially subtransient reactance will be present, then transient reactance and then steady state reactance. So if the time delay is there, reactance also changes. So positive sequence impedance, if considered for 3 to 4 cycle transient, then it will be represented by JXD dash, that is transient reactance. And if, in case of the steady state condition, it is represented in terms of the Z1 is equal to JXD, where XD is nothing but direct axis reactance. Now, if the machine short circuit takes place from unloaded condition, the terminal voltage constitutes the positive sequence voltage. On the other hand, if the short circuit occurs from loaded condition, the voltage behind appropriate reactance, that is subtransient, transient or synchronous, constitute the positive sequence voltage. So here figure shows the three positive sequence network model of synchronous machine. Here Z suffix n, that is neutral impedance, it does not appear in this model because IN is equal to 0 for positive sequence current. Since it is balanced network, it can be represented by the single phase system also. So if we consider the three phase model, see EMF for all the phases shown in series with the impedance, that is positive sequence impedance Z1 with phase A, EB and EC respectively. So if we have to represent the same model in terms of the single phase model, then it will be EMF in series with the impedance, and voltage is applied across the this EMF and reactance. So what is the formula for positive sequence voltage? Va1 is equal to A minus Z1 into IA1. Sorry, Z1 into IN. Now, negative sequence impedance and network. So we had discussed the first part, one sequence network, that is positive sequence network. Now for the same synchronous machine, we have to calculate the negative sequence impedance and network. It has already been seen that a synchronous machine has zero negative sequence induced voltage. With the flow of negative sequence current in the stator, a rotating field is created which rotates in the opposite direction to that of the positive sequence field, and therefore a double synchronous speed with respect to the rotor. Current at the double the stator frequency are therefore induced in the rotor field and damper winding. In sweeping over the rotor surface, the negative sequence EMF is alternatively presented with the reactances of the direct and quadrature axis. The negative sequence impedance presented by the machine with consideration given by the damper winding is defined as Z2, that is negative sequence impedance. Z2 is equal to JXQ double dash plus XD double dash upon 2, where XQ double dash is nothing but quadrature axis subtangent reactance and XD double dash is nothing but direct axis subtangent reactance. And if we according to the formula also, we will get the idea that the value of negative sequence impedance is always less than positive sequence impedance. And negative sequence network model of a synchronous machine on a three-phase and single-phase basis are shown in figure. The reference bus is of course at neutral potential, which is same as that the ground potential. So if we consider the three-phase model, the negative sequence impedance of each phase are shown. Here EMP is not present. So three reactances are shown, and current IA2, IB2 and IC2 are flowing through the phase A, B and C respectively. And if we convert this three-phase model into the single phase model, it will be Z2, and voltage is applied across the Z2, and reference bus is nothing but neutral bus. Current IA2 is flowing through the phase A. And if we go through the relation between this negative sequence impedance and voltage, Va2, that is negative sequence voltage, is equal to minus Z2 into Ia2. That is, it is multiplication of the negative sequence impedance and negative sequence current. Now, last network is zero sequence impedance and network. We state once again that no zero sequence voltages are induced in the synchronous machine. The flow of zero sequence current create the EMF which are in time phase but are distributed in space phase by 120 degree. The resultant air gap heat caused by the zero sequence current is therefore zero. Hence, rotor winding present leakage reactance only to the flow of zero sequence current. And if we go through the relation, or we are going to compare the positive, negative and zero sequence component, zero sequence component or zero sequence impedance is always having less value as compared to the negative sequence impedance, and negative sequence impedance is having less value as compared to the positive sequence impedance. So zero sequence network model on three phase and single phase basis are shown in figure. Here we show the impedance, zero sequence impedance of each phase with which are connected to the neutral, but in this case the neutral impedance is also present, which is represented by the Z suffix n. That is, the current flowing in the impedance Zn between neutral and ground is In is equal to 3 into Ia0, where Ia0 is zero sequence component of the current Ia. The zero sequence voltage of terminal A with respect to the ground, the reference bus is Va0 is equal to minus 3 Zn Ia0 minus Z0 G Ia0. That is, it is equal to minus of 3 Zn plus Z0 G into Ia0. So, if we consider the single phase model, in this case 3 Zn, that is impedance of all the three phases, and in addition the neutral impedance will be in series with it, and voltage Va0, that is negative sequence voltage, is applied across these phases, and reference bus is nothing but neutral bus. So if we see the formula, Z0 is equal to 3 Zn plus Z0. And what is the relation between this zero sequence impedance and zero sequence voltage? Va0 is equal to minus Z0 into Ia0. That is, negative sequence voltage is nothing but it is the negative multiplication of negative sequence impedance and negative sequence current. Okay, now the next point is representation of the power system component in term of the symmetrical component. So in this power system component, mostly for your syllabus point of view, we will discuss the representation of the or sequence impedances of the transmission line. That is, we had already discussed about the sequence impedance for the synchronous machine. Now next point is sequence impedance of the transmission line, and for the examination point of view, there is a repeatedly asked question: prove that for fully transposed transmission line there is equal positive and negative sequence impedance. So what is the relation between positive and negative sequence impedance in case of the transmission line? Equal positive and negative sequence impedance. And another one conclusion is that zero sequence impedance is much larger than the positive sequence impedance. In exam, there will be question: prove that this statement equal positive and negative sequence impedance and zero sequence impedance is much greater than the positive sequence impedance in case of the fully transposed transmission line. So now we will discuss the sequence impedance of the transmission line. See, through the diagram it is clear that the self reactance, that is XS, here S is suffix is for self reactance. So self reactance of each line, that is line A, line B and line C are shown, and current IA, IB, IC are flowing through the line A, B and C respectively. XM is the mutual reactance between the any two phases, that is between the phase A and B, phase B and C, or phase A and C. And VA, VB, VC are the voltages, that is supplied voltages at the sending end of the transmission line, and VA dash, VB dash and VC dash are the received voltages at the receiving end of the transmission line. Whereas neutral wire is sufficiently spaced from the main lines lines A, lines B and line C in such a way that we can neglect the mutual reactance which is present between the line A, line B, line C and between the neutral line. So and the current flowing through the neutral line is given by the formula IN is equal to IA plus IB plus IC. So if we go through the relation from the diagram, it is clear that the voltage difference between the sending end and receiving end voltage, that is VA minus VA dash, is equal to voltage drop between sending end and receiving end, that is J into XS into IA plus J into XM into IB plus J into XM into IC. That is, we consider the voltage drop because of the self reactance as well as mutual reactance of the line. Then similarly, the voltage difference between sending and receiving end in case of the line B, VB minus VB dash is equal to J into XMIA plus J XSIB plus J into XMIC. And voltage difference between the sending and receiving end in case of the line C, PC minus PC dash is equal to J into XMIA plus J into XMIB plus J into XSIC. And if we represent this relation or these three equations in terms of the matrix form, the VA, VB, VC matrix minus the matrix VA dash, VB dash, VC dash is equal to J into 3 by 3 matrix, that is X, XM, 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 XS, XM, 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 XS into matrix IA, IB, IC. Now here VP minus VP dash is equal to JD into IP, capital A in bracket VS minus VS dash is equal to JD into capital A into IS, and VS minus VS dash is equal to A inverse of JD into A into IS, that is A inverse JD is equal to 1 by 3. We will get this equation, and if we solve this equation at the end, we will get the voltage difference, that is V1, V2, V0, positive, negative and zero sequence voltage at the sending end side minus V1 dash, V2 dash, V0 dash, that is positive, negative and zero sequence voltages at the receiving end side is equal to J into reactance matrix into current matrix, where I1, I2, 0 are the positive, negative and zero sequence current. Then at the end we will get the relation that positive sequence impedance for the transmission line is given by the formula J into XS minus XM. Negative sequence impedance, that is Z2, is given by the formula J in bracket xs minus xm, and zero sequence impedance is given by Z0 is equal to J in bracket xs plus 2xm. And from once you derive up to this point, now you can conclude that for fully transposed transmission line, there is equal positive and negative sequence impedance, which is clear from the formula also, that is Z1 is equal to Z2. And last comment is zero sequence impedance is much larger than the positive or negative sequence impedance, and it is also clear from the formula. Now you have to represent this sequence impedance in terms of the phasor diagram, uh, or in terms of the positive sequence network, negative sequence network, and zero sequence network. So positive sequence network are shown here. Phi1 is the sending end voltage in figure A. Refer figure A. Phi1 is the positive sequence voltage at the sending end. Phi1 dash is the positive sequence voltage at the receiving end, and current I1 and Z1 are the positive sequence current and impedance respectively. In other phase diagram B and diagram C, only the parameters are represented in terms of the negative sequence impedance. It is represented by the suffix 2, and in terms of the zero sequence network, it is represented in terms of the suffix 0. That is, the decoupling between sequence network of a fully transposed transmission hold also in a three-phase synchronous machine and three-phase transformers. These facts led to the considerable simplification in the use of symmetrical component method in unsymmetrical fault analysis. In case of the three static unbalanced impedances, coupling appears between sequence network, and the method is no more helpful than a straightforward three-phase analysis. So now, till now we have discussed representation of the synchronous machine and transmission line in terms of the positive, negative, and zero sequence network in case of the unsymmetrical fault. And from this representation, it is clear that although in case of the unsymmetrical fault creates the system in unbalanced condition, but it can be represented in terms of the balanced condition with the help of the sequence component, and that sequence network are more simple, are present in more simple form, and that's why it helps to correct power system analysis. Now the last point of the today's lecture, will discuss one numerical based on this point, that is how the positive and negative zero sequence component helpful to find out the fault current. So here we'll consider the one example. What is the given data? 10 MVA 6.6 kV three-phase star-connected alternators are operating in parallel. Refer the diagram 3.27. That is, three generators which are star-connected. They are operating in parallel, and each has X3 double H, that is subtransient direct axis subtransient reactance is equal to 15%. X2, that is negative sequence reactance, is 12%, and X0, that is zero sequence reactance, is 4.5%. If an earth fault occur on one bus bar, that means it is the example of unsymmetrical fault. Make sure that whenever you are going to solve the numerical in exam, first of all confirm the type of the fault. According to that, confirm whether it is the example of symmetrical fault analysis or it is the example of unsymmetrical fault analysis. So in this case, if an earth fault occur on one bus bar, determine the fault current. There are three conditions. You have to calculate the fault current only, but you have to calculate that fault current for three conditions. First condition, when all the three alternators are solidly grounded. This is the first condition. Second condition, when only one of the alternator is solidly grounded and others are isolated. And third condition, when one of the alternator is grounded through an inductor of 0.3 ohm and the others are isolated. So we will start to solve the numerical. First of all, since we have to deal with the per unit quantities, let us consider the base MVA, that is base power is 10, and base kV, that is base voltage, is 6.6. Then induced voltage EA is 1 plus J0 per unit as per the assumption of the unsymmetrical fault analysis, and it is equal to 6.6 root 3 kV actual. Now full load current of the each transformer is nothing but power upon voltage, that is 10 into 10 raised to 6 upon root 3 into 6.6 into 1000, because we had converted power into the volt ampere, that's why it is multiplied by 10 raised to 6, and we had converted the voltage into the volt, that's why it is multiplied by 1000. So current will be 875 ampere. This is the full load current of each alternator. Now these three alternators are connected in parallel. So we'll consider the first condition. What is the first condition? When all the three alternators are solidly grounded. Now since all the three alternators are operating in parallel, the resultant reactance will be 1/3 of each. So positive sequence component Z1 is equal to, what is the actual reactance they had given? 15%, that is J0.15. But since three alternators are operating in parallel, it will be J0.15 upon 3, that is J0.05 per unit. That is the positive sequence impedance. Now negative sequence impedance Z2 is equal to, what is the negative sequence impedance? X2 is reactance is 12%, that is J0.12 divided by 3, it will be J0.04. And zero sequence impedance Z0 is equal to, what is the zero sequence reactance given? 4.5%, that is J0.45, J0.045 divided by 3, since three alternators are operating in parallel, so it will be equal to J0.015 per unit. That is we had calculated the positive, negative and zero sequence impedance in terms of the per unit values for the first condition. In exam, if they had asked in the values in terms of the ohm, then we have to convert these per unit values as per the selected base value of the power and voltage into the actual unit. Now what is the question? We have to calculate actually fault current. So fault current IF is equal to IA is equal to 3 into EA upon Z1 plus Z2 plus Z0, because total impedance is nothing but addition of positive, negative and zero sequence impedance. So it will be 3 into EA is equal to 1, because for the unsymmetrical fault analysis we consider the EM equal to 1 per unit. So 3 into 1 upon J0.05 plus J0.04 plus J0.015. So it will be equal to minus J 28.57 per unit. And since you are having the idea about base value of the current, you can calculate this value into the actual value also. So that current will be minus J 25,000 ampere. That is for first condition, the fault current is minus J 25,000 ampere. Thus symmetrical component help to make easier calculations. It converts complicated system into the simple system for the symmetrical fault analysis, and because of that we could calculate the fault current in the first case. Now for the second case, what is the second case? Here what is the change? Only one of the alternator is solidly grounded. That is, suppose we consider the example, if you refer the figure 3.28, the only first alternator is grounded and other are isolated. In this case, positive sequence impedance will be same, J0.05, negative sequence impedance will be same, J0.04. But in case of zero sequence component, that we have to consider the 0.045 per unit reactance. So what is the, in first case it is J0.015, but it is, since grounded, we will not divide it by 3 and it will be J0.05 per unit. So remaining procedure is same. We have to use the same formula. IF is equal to IA is equal to 3A upon Z1 plus Z2 plus Z0, and you will get the current in per unit minus J22.22, and in terms of the actual unit minus J 19,440 ampere. That is, in second case, since negative sequence impedance changes, and because of that the fault impedance is fault current is changed. And what is the last condition? When one of the alternator is grounded through an inductor of 0.3 ohm, that is, in the grounded wire they had added the 0.3 ohm inductor. So refer this diagram 3.29. Suppose we consider that alternator is first one only, then 0.3 ohm is added in case of the neutral wire. So what will be the change? Positive sequence impedance will remain same, Z1 is equal to J0.05 per unit. Then negative sequence impedance will remain same, Z2 is equal to J0.04 per unit. But in case of the zero sequence impedance Z0, here original reactance, that is J0.05 plus J3 into 0.3, that is 0.3 is added, then 3, because 3 generators are present, and into 10 upon 6.6 bracket square, because as per the change of base value, it will be multiplied by MVA base upon KV base, KV voltage bracket square. So 10 into 10 upon 6.6 bracket square. So J 0.2516 per unit. Now again we have to use the same formula for fault current. IF is equal to I is equal to 3 into E upon Z1 plus Z2 plus Z0. You have to put the value of Z1, Z2 and new value of the Z0, and you will get the current in per unit, that is minus J 8.7822, and by using the base value of the current 875 ampere, you will get the actual value of the fault current, which is equal to minus J 7684 ampere. So thus we had used the positive sequence component. In today's lecture we have discussed that what is meant by the symmetrical component, then what are the phase sequences of the symmetrical component, then what is the relation between them, what are the formula for the positive, negative and zero sequence impedances, and how to represent the major power system component like transmission line, synchronous motion in terms of the positive, negative and zero sequence network, and we had solved the one numerical. Okay, and in next lecture we will cover the point related to the synchronous related to the representation of the symmetrical component for different type of the unsymmetrical fault like line to ground fault, then double line fault, etc. So that point will be covered in the next lecture. Thank you.